So now we have already seen the thread libraries, that there are two primary ways to implement kernel, which is entirely in user space, and the kernel libraries which are supported by the operating systems. We will go to the threads, the three threads which we have studied: pthread, Windows, and the Java threads. Will go to these threads one by one, and we'll see the details of each threading. So this pthread may be provided either by a user level or the kernel level. So both level threading can be implemented using the pthreads. Its standard is IEEE 1003.1c. It's API standard, and this is a specification, not an implementation. It means that we provide some specification while implementing these, while programming these threads, but it's not we implement the threads from very beginning, because the threads are already implemented using the APIs, and we only give the specific data to these threads for implementations, and this manages everything by itself. So APIs behaves differently for different type of libraries. Implementation is up to the development of the libraries, and the common Unix operating systems such as Linux, Mac OS uses the pthread libraries. Okay, and also if we see some example of pthreads, then if we go into the pthreads now, for example, if we have an example, let's take here an example, and let's say that we want to get the sum of a number of an array where the array has n number of elements and each element is increment power. Okay, so we want to perform this task in parallel using multithreading. Okay, so there are four attributes, four we can say that functions of pthread init, where we initiate the pthread, and pthread create. Here actually we provide the initialization of the attributes, and we create the attribute, and then we join, and after we join we just exit from pthread. So we have these four main functions of the pthread. Okay, now here you can see that there's a main. Here we can see that here is the signature of the thread we want to implement. So this is a runner, a wide runner, and it gets some parameters, and we have thread ID, we have thread attributes, and now here we create the thread, and then we wait for thread. Here we actually set the default attributes of the threads, and then we create the thread using the parameters like thread ID, the attributes, and we call this runner method, right? And we pass the arguments we received from the thread class. Okay, the thread function. So, and then we print here the sum of the elements of the array. Here we can see that we have a function, that same function, the signature we defined before, is actually implemented here using pthread wide runner parameter. In parameter we get string usually, so all ASCII to integer. This function is a to I is actually ASCII to integer conversion. It's a conversion function. Okay, so the upper means that whatever the parameter, what means if we have given this 5, then 5 is the upper limit. Okay, this is an upper limit. Okay, so this is actually converted into the integer. Okay, into the integer type, and then the sum here, sum for now the sum is 0, and here we see that we have a loop here, and up to the upper limit means 5, and every time we increment this by this I. Okay, and we add the I into this sum, right? So we add the elements of this input, right? If we have given 5 means 5 plus 4 plus 3 plus 2 plus 1, right? So actually it goes from here to here. It means that the sum is 15. Okay, so for this the answer is actually 15. But once this is completed, the thread is exited. So this is an example of pthread library. The implementation is done in pthread, and if we go into this, first suppose if we have multiple number of threads, then what is different that pthread we define the array of the threads, maybe a numbered array 1 to 10 maybe. Okay, so we define the array of the thread here, and while joining, then we will count on all the threads of available in this array 1 by 1, right? 1 to maybe 10, right? So this is how the multiple threads are handled in pthread. Okay. Next, in Windows we have some different approach. This is the example 2. Example 2, right? For the same example, for the same summation problem, right? Okay. So here the D word, this is the D word is actually Windows thread library parameter, the data type. This is the data type, and for the Windows thread, which means the double word, right? The double word has it actually holds the unsigned integers, right? Unsigned integers, which ranges from 0 to a very large amount, something like that, right? A very large range. And you can see, you can just Google it and you can see the range if you are interested in this, right? So for that range it can hold the integer. So D word sum, summation, whatever the number you give, the summation is stored over here. And when we have summation and LP wide is actually pointer to wide object. It is a pointer to wide object. LP wide is actually a pointer to the wide object, right? So this pointer to the wide object is here for the summation function, right? We have the upper level which we have entered here as a parameter would be converted in the word, right? And then this loop is executed for the summation, right? Once this loop is executed, and we can see here, take pen is more efficient, it's more convenient for me to use the pen here, and this is thread ID and thread handle and parameters. Now here we create a thread, and it has some parameters, the default security, which is null here, and default stack size defines 0, which is actually assigned at the time of execution, and summation, the method we have created previously, if the function is called here, the function which we have created is called over here. Okay, and then the parameters of the thread are passed over here, and then default flag we set it 0 and the thread ID. Okay, and then this wait for the single object for the infinite time. Now I must tell you that there are two type of threads. There are asynchronous and the synchronous threads. Now asynchronous threads here the parent thread resumes after creation of child. In asynchronous threading, parent resumes after creation of child, while in synchronous threads, the parent wait for child or maybe childs to complete first. Okay. So here the infinite wait means that this is actually asynchronous. Synchronous thread. Okay. And then once all the parts of threads are returned, then this thread would be closed by this close down. Okay, and then print the summation. Now we have also Java threads. We know that I might already given you an assignment about the Java threads. So it is implemented by two approaches. One is inheritance, where we use extends, right? Another is runnable interfaces. Okay, so there are two approaches for implementation of threads in Java. We implement runnable, and we say run I'm a thread, and then creating thread. For creating a thread we say thread worker, this is a thread name, and the object of thread is inverted, and then for starting of thread work data start. This is a function call. We can say function call. It might be if it is inside, if it is for the kernel, it is a system call. If it is for the user space, then it is a function call. Okay, waiting on a thread, and this is a try catch block. We know try catches are exceptionally. For example, if any exception happens in between while executing this thing, and this interrupt would be called instead of the blockage of whole program. So this throws only exceptions. And also we have some frameworks for executing, and here's the example of those frameworks. So now after Java, this is actually I'm going through Java like that very fast, because we already I remember that I have already given an assignment to you for the Java threads. But if there are two sections actually, so if you have not received any instruction about this assignment, if you don't have any instructions about this assignment, then I will repeat that assignment, and it would be the date it is required to submit by the next class, when the online session would be conducted for your class. Okay, so we say that the your assignment may be, let's say I say assignment is implement the Java thread. Right, using both approaches. The inheritance and runnable interfaces. Okay, so you have to implement this. You have to work on some programming, take your computers, do some code here, and implement the example of this summation. Same, the summation example. Okay, so if I give any number of upper bound, then it will sum all the numbers will in that bound for me. Okay, so you implement this example using both approaches. Okay, this is your assignment. I remember it's assignment 2, but maybe we have already lost a lot of things, so it's assignment 1. So implicit threading, and now as threading is not an easy task, I have already told you, so we have now a different approach to deal with the threading, and because there are two more main problems with threading, which is creating multiple threads, that when to break the thread, when to how to balance the split, and how to divide, and how to share the resources, how to share the data. So these all are very difficult tasks for programmer to measure and to perform. So we have some good news for that we have some implicit threading approaches which is growing in popularity as the number of threads increase. Now in one program we might have multiple threads. Even if you see this screen, then in this screen we have voice, we have video, we have text, we have a pen, we have a tablet, we have multiple sort of inputs like keyboard, we have mouse, we have tablet. All sort of inputs are available, are working simultaneously, and we have text also, we have images also. Everything is displaying, everything is managing, and we have also recording voice, recording videos, PPTs are running. So you can see that only this screen which you are seeing currently has a huge number of threads in itself. So how these multiple threads are working correctly, to explicitly do these tasks to work correctly, is a difficult task, and implicit threading actually made this complicated situation easier for us, and now we can implement the thread using implicit threading approach. In implicit threading approach, we have some libraries, and we have some actually fun methods for this threading, where we have where these threads can be implemented and managed by itself, or managed by some existing functionalities. So we have thread pools, number 1, where we have multiple thread pools. Instead of creating the threads explicitly, we have a pool of threads available in our system. We have fork join, where we divide this task into multiple threads, and then join them. And OpenMP and Grand Central Dispatch, it's a make and Intel thread building blocks, right? So we have different type of approaches for this implicit threading. So thread pool, what is thread pool? I must just draw a diagram for you, that for example if I might have a queue. Let's say here are the incoming tasks. Tasks are incoming from here, right? And they are queued up, maybe 2, 3, 4, right? They are queued up into a queue, right? Wait queue. So this is a wait queue. Now we have a pool here. Now you might remember I already told you in the start of this lecture that I will tell you that what is the thread pool while I was talking about the server architecture, client server architecture. So here is the main concept of that. So we have maybe thread 1, and we have thread 2, and we have thread 3. So this one task, maybe we can say this is task 1. Okay, so it is sent to a thread. Maybe if I just let me see. Oh, I'm sorry, it's gone. So what I was doing that if there's a task from queue, it's coming here, and we can have well, sorry. So here's the task, and here's the pool, right? T1, T2, and T3. These are thread pool. This is thread pool. Now each time, this task will take one thread and it performs some task, some service. It provides service to that thread using this thread, right? Once this service is done, the task is dispatched, and thread which were taken from here is put back over the pool, returned, right? So we have now limited number of threads. We have now limited number of threads allocated to a specific application. Right? This is one of the major benefit of the thread pool, that you can specify a number of threads for a pool for a specific application. So we have maybe 3 threads for this type of application which we have here. Maybe this application, right? Okay, so this application might be creating 1 task or 2 tasks or maybe 3 tasks, and each time only 1 thread is each time from this number of threads, maybe 3 threads, each time 1 thread or maybe 2 thread or 3 threads can be utilized for service, but not more than 3 threads would be allocated because it has some limitations. Okay, so there are 3 methods: a new single thread executor, and a new fixed thread executor, and new cached thread pool, right? So these are 3 thread functions for this. Now I was talking in this example for this fixed size, where we have the size of maybe 3 threads should be belong to this application only. Okay, now here we have Java threads and Java thread pools. You can see that we have executor here, a new cache thread pool here. Okay, and it executes some code. Okay, and when it shut down, it actually stop receiving new task. Okay, and while it is also, it continues to finish the task already received. Okay, now here we have again fork and join. This is another very popular parallelism concept which is implemented for for many multi-thread operations. Even in client server architecture, this is also very popular approach. Okay, so fork and join. Fork is actually like the fork, traditional fork. We have a fork here, right? So actually you have one thread coming from here, and you create multiple. You have one task, and maybe you creating multiple threads from that. Okay, so this is the same here. That we have a main task here, and you divide that. And this fork join approach divide the task into the multiple forks. So one portion is resolved over here, another portion is resolved over here, and then once this is, let's say, service portion being served here. Okay, and once these are being served, the complete served, they are joined as again a task. This is task. This is task. So while these are in service, they are broken into the parts. Now currently in Bitcoin mining, right? People are Bitcoin mining. People have created mining pools, which means that every time they receive one block to mine, they divide that block into multiple servers, because this mining is heavyweight process, so they divide into multiple servers to perform in parallel for beating the time. Okay, maybe within 10 minutes they complete this mining. Okay, so once this is completed, they again join this to make a new block again, to make the same block which was received here from here. Okay, so this is a very popular concept nowadays. You can very popular example for your fork join approach, and this is most advanced example. It will go for years with you, I believe. So fork and join, actually here we have subset of a task, subtask. We call it as a subtask, as I already told you. So this is portion 1, this is portion 2. For example, if an array, then this array is broken like this, right? And then task 2 would be in that 2. Right, this is just an example. It might have different approaches inside this. Forking and forking approaches might be different, but this is generally how it works. Once this is completed, now here, if we have a 0, the array size with n number, then it is passed, and these two are performed in parallel. It should be coming from here, but I'm doing from here. Once it is done, it is again combined to represent as a one array, not the two parts, but it is again joined. So this portion is forking, and when you join the two parts, is called as a join. Okay, now this can be hierarchical, this can have a hierarchical structure also, like this. Now this is a task which is forked here. Okay, this task is further forked over here. Now once this is completed, it is joined over this to now this task is forked here, right? Now once this task is completed here, it goes back to the task 1. This task again return to the task, this task 2, right? And this task is completed hierarchically. So here when it goes to this direction, it is actually forking, generating multiple tasks. This task again generates multiple tasks. This can also generate some other multiple tasks, right? Right, so this can also generate multiple. Once it is done, it is joined back. Actually this is 4 and this is joined. Okay, so well, this is also a concept of parallelism, where you have a number of tasks divided into subtasks, which is further divided into subtasks, like a hierarchy, right? So for join parallelism, I already told you the same example previously. Okay, and this is the implementation of this to compute the summation, and the same example is done by this fork join. Now I tell you there are two portions for a fork, that left and right. Okay, you have a left side, left task, and you have a right task. Okay, this is main task. So this is called left and this is called right. Mostly we use this nomenclature. This is a nomenclature. You can also use your own, but this is a nomenclature used in the programming approaches mostly. Once this is done, you join these left and right here. Okay, so here we have also, we can see that this is the left and this is the right portion. Okay, now another approach is OpenMP. Now we have seen the threading tools and we have also seen the fork and join. These are two very important concepts. Now we have also further other methods of implementing to respond to threading issues, right? So OpenMP is also one of the API for C or C++, and it provides support for parallel programming in shared memory environment, and so we don't need to have any complicated implementation here, but we just use this header file and we call this in the sequential code, in this code, right? So this is the parallel code, while this is a sequential code. Here is the sequential code, sequential, and here is the sequential code goes, while this code is parallel code. Okay, so this is actually the identifier for the parallel region. So it knows, OpenMP now knows that this part need to be broken. Okay, this is a block actually. And this can also be run for a loop also. So if you have one a single statement, or you might have multiple statement, or you can might have also loop which can would run in the parallel. So you just need to use this identifier for the parallel. Okay, but instead of only this program OpenMP parallel, we also add for that. This is for for loop, so this is for loop. Okay, and then we have Grand Central Dispatch. This is another approach like OpenMP for the macOS and iOS, and this has a block identifier, right? This is a block, and the block inside this is executed in parallel. Okay, and we can have different type of queues here: interactive, initiated, and utility, and also background queues. Okay, so we have serial queues and concurrent queues, where a serial queue is here like this. Sorry, if we have, sorry now if we have a queue here, it is a serial queue, right? And we take one by one object, we take one by one task here, and we perform some processing here, and then dispatch here, and then we take another, and then we take another, then we take another, right? This is the serial. While the concurrent might have multiple serving portion here, we take one here, like this is a queue. One is taken here, another is taken here, another is taken here, right? So this is a concurrent FIFO. So the queue is still FIFO, and the queue is still FIFO here also, but this is a serial implementation, and this is a concurrent implementation. This is a concurrent implementation. Okay. So here are some queues, queue code, code for you. You can see the example here. Okay, that how a specific queue is initiated. Okay, with a specific size, like size 0 here is shown, and also we have Intel Thread building block TBB, known as TBB. This is also a library designed for parallel C++ programs. Serial version of loop can be seen here, and the parallel version is seen here, right? Now if we see serial version, and then we just implement this apply with this apply queue, apply function, and this while it's parallel, it will go like this. Alright, we say parallel for, and for serial for we don't have any identifier here, no identifier. And for serial for parallel we have an identifier. This identifier is actually works as a tag file for suppose in sometimes if you write something in your file using programming, then you say, okay, if this comes, then break the line, right? If there is, for example, if programming, then if this comes, then don't read, right? Because it's commit. So as this is an identifier, this is also an identifier for parallel. Okay. And now we have threading issues. Now inside these threading approaches, we also different threading issues we need to address. Now, forking and executing, these are two system calls. In fork system calls, if okay, now the function of these two calls is actually the for fork. If I say for fork, is to create a separate process, or maybe duplicate process. Now this is a work of fork system call. Now for the execute system call, right, it replaces actually, and the parameters used will replace the process. All the threads will be replaced. All the available threads will be placed here. Now, if execute wouldn't call afterward fork, then it will duplicate all. If execute is called immediately after forking, then only the fork that invokes new version will be duplicated. For example, let's say here is example. Let's say this is an example, right? And I have called fork function, and some statement goes here, and the fork, and some statement goes here, right? And then I say execute function. Now in this case, it duplicates the execute function, actually duplicates all the thread. Okay. While if we say that another example, fork, right, and statement and execute, in this that only sorry, also we for suppose we have another fork here, another execute here, and this doesn't go here, this goes here, right? Then this execute only invoke this fork, right? This execute only invoke this fork, right? It does not duplicate, but it provides a new version of fork, right? So this is what the execute and system call semantics for the fork. Okay, we have also this is some more details about that. Signals, we have all two type of signals coming from the system. We have default signals and user defined signals. So default signals belong to the kernel, while user defined signals belongs to the user. Okay. Now, what is a signal? Signal is actually an occurrence of an event. For suppose click events, right? This is an event. It is actually generated as a signal, right? So any occurrence of any event, input data, right? It's also an event. Keystroke, it's also an event, right? Maybe notifications, it's also an event. It's also a signal. So incoming signals, handling the incoming signals is also a type of multithreading, right? For suppose even if on a system, if I'm delivering a lecture on this system, suddenly if over this top, if I receive a notification, right? Though all my notifications are actually blocked here, but if I receive a notification maybe of update, right, update my OS, then this is also a signal coming from my system. Maybe it is coming from kernel level, or maybe it is coming from the user level. So when we say default signals, it actually belongs to the kernel. When it is coming from the user level, then it's a user defined signals. Okay, for example, if it is system update, it's a kernel signal. For example, a message coming from a friend, right, using maybe WeChat or maybe WhatsApp, right, application, then it's a user defined, because it is coming from an application, not from the kernel. Okay, so this is a user defined. So two type of signals, and these two signals are handled as a thread while you are in execution of another type of threads. Okay, and this thread is done actually because of the the pool of the thread pools, because in the system we have a specific number of threads belonging to one pool, right? For example, I have created a pool which have maybe which can handle 3 notification for MS Word, which can handle 3 notification for my chat room, which can handle 3 notification for my PowerPoint, and 3 notification for some other sources. So at any time a signal can come from any application or any system. Okay, so this is just details of those threading. And now we have also cancellation of the threads. When thread is created, sometimes it is required to terminate it. Most of the time, every time a thread is created, actually it requires to terminate. Now this termination can be in 2 modes, synchronous and asynchronous. Okay, when we say asynchronous, it means that it is actually done manually. While we are creating a program, we let's say we have one thread executing, and when it is completed, we say it is completed, then terminate the thread. Okay, this is done manually. And another is deferred cancellation, allows the target thread periodically check if it is if it should be cancelled or not. Now this is a normal thread when we know where is the end, we know about the end. But when we don't know about the end, we have deferred cancellation. Now here we have a routine check if it is terminated or not. Okay, if it is terminated or not, we have to check this every time, repeatedly. Okay, this belongs to deferred cancellation. Okay, now here is cancellation thread, b thread cancel. Okay, and wait for thread to terminate. Okay, now here we know and here we don't know the thread to terminate. So we have different we have deferred cancellation and asynchronous cancellation, as I have already told you. Okay, and in many systems it is also handled through signals. For example, sometimes if we start downloading a file, then we know that okay, this file size is maybe 5 MB. We know that this file size is 5 MB, and then the process, we can see the process. Okay, as long as it's downloading, we see that it is completing, it's completed now. But if we don't know the file size, then what happens, that we can see that 1 kbps. Okay, what maybe one is very low. You will laugh on me that 1 kbps what kind of internet I'm using. So 100 kbps. Okay, now in this you don't know, then we have a routine thread which is checking every time if it is completed or not. Once it has completed maybe 5000 kbps, right, 5000 kilobytes, right, it is completed, then shows it's completed, right. So we have known, here we have known, and here we have unknown size. So in such scenarios, we use signals. Okay. In Java, these threads are cancelled by using interrupts. I told you already that there are interrupts, hardware interrupt and software interrupts. So when it comes to software, then in threads we have different type of interrupts. So interrupted, if we want to interrupt a work, we just call a system call. We just put a system call, a function call, method as an interrupt, right? And if we want to check if the system has been interrupted or not, then there is a method is interrupted to check to see if the system has interrupted or not. Okay, and then we have also thread local storage right here. Okay, have its own copy. Every thread has its own copy to save. Useful when you don't have a control over the thread creation process. Okay, it is mostly utilized in the threading pools. This is actually a server level. They create their own local storage. For example, if I go here, that if I have a data center, right? If I have a data center, maybe one in California, one in UAE, and one maybe in another state. Okay, maybe Canada. Okay, whatever, or maybe Pakistan. We don't have any data center, but let's say in Pakistan, whatever. So now if we have one task and maybe it is shared over here, but due to some if the task is heavier and everybody is working, maybe in the case maybe it has some data to take from different data centers, right? Data center 2, data center 1, and data center 3, right? So maybe it requires data from multiple data centers. Now every data center should save the local copy of these threads, whatever they're coming to there. Maybe all thread information is coming, but it saved all thread information to itself, right? Thread information is saved locally here. All the thread information is saved locally to those. Okay, and then scheduler activation, we have an activator here. Okay, actually in both many to many and one to one. Okay, sorry, one to one like that. I'm using this wrong. Okay, many to many and one to one level models requires communication to maintain the appropriate number of kernel threads allocated to an application. So for achieving this, we have a lightweight process here. It actually takes care of schedule activation. Okay, this is actually in between user and kernel level threads. This is there is a thin line in between user level and kernel level. Okay, so this is a lightweight process. We call it scheduler activation. Okay, now for Windows we have different threads, and we have also already seen a lot of threads, but here if you see that we have thread blocks, different thread blocks for different type of thread: execute thread kernel block, and thread environment block. So we have these three thread. This is the user space and this is the kernel space threads. These are kernel level thread, and this is the user level thread. Okay, and in Linux we have similarly we have different threads like file system, the memory, and signal handlers, or maybe files. So this is what all about the threads. We have seen multiple threads and concurrency in this lecture. Okay, and we were seeing that how threads are implemented, how threads, what are the threads applications. Firstly, we seen that what are thread applications, and then we seen that what are the types of threads, what are the models of threading, and then we went to the programming real thread. We seen three different type of threads, like we have seen P threads, we have seen Windows threads, and we have seen the Java threads. For P threads, we explored that this type of thread belongs to the Unix, Linux, or Macintosh operating system, while the Windows threads belongs to only the Windows operating system. Now, P thread has both type of threading available on the user level thread and the kernel level thread, while the Windows level threads have only the kernel level threads. And we have another approach of Java threading. Now, Java threads are actually implemented by JVM, Java Virtual Machine, which has a capability to provide a virtual environment where it can adopt the host type, whether it's a Windows operating system or it's a Linux operating system. Any type of operating system can be adopted. So it means that Java Virtual Machine actually provides it is actually a facilitator to implement either P thread or window thread, because on any system, if you have a Java, it knows the underlying logic of the instruction sets, and it goes like that, right? In over the Macintosh or over the Linux system. On the Windows system, it knows the underlying logic of the instruction set, and it goes like that, right? For the specifically Windows. So these are three type of threads we concerned about, and we have seen the approaches for the threads. We seen implicit threading. We have seen that implicit threading, because threading is a complicated process, so we have implicit threading. In implicit threading, we have seen fork and join. We have seen threading pools. We have seen OpenMP. We have seen thread Grand Central Dispatch and Intel thread building block, right? And lastly, we have seen some examples of this threading in Windows and in Linux operating systems. So this is all about today's lecture, and with this lecture, I have also provided you a link for the meeting on Zoom. Maybe we can I will discuss with the coordinator, and will give you the schedule for that meeting. Okay. Wish you good luck. If you have any questions, just note down those questions. We will see those questions in our online session. And remember, this online session is very much important, because you need to do some assignment. Like I have already given you assignment. We'll discuss that assignment. We'll see that assignment. I'll see that assignment, and I will mark you. I will give you grades on that assignment, and also each lecture you attend will be credited with 1 mark. Okay. Wish you good luck. Wish you safe. Stay home. Stay healthy, and stay safe. Thank you.